Resilience achieves historic milestone, successfully enters lunar orbit with precision maneuvers.
On May 7, 2025 at 5:41 a.m. Japan Standard Time, May 6, 2025, 2041 Universal Time Coordinated, the Resilience lunar lander developed by the Japanese company ispace successfully entered lunar orbit, marking a significant milestone in its mission 2 as part of the HAKUTO-R program. This achievement is a testament to the meticulous planning and execution of orbital maneuvers, showcasing ispace's dedication to advancing lunar exploration.
Launch and mission overview.
The journey of Resilience began on January 15, 2025 when it was launched aboard a SpaceX Falcon 9 rocket at 6:11 and 39 seconds Universal Time Coordinated. After a successful deployment from the rocket at 7:44 and 24 seconds Universal Time Coordinated, the lander embarked on a low-energy transfer orbit strategically designed to minimize propulsion requirements for reaching the Moon.
Following a lunar flyby on February 14, 2025, where it reached a maximum distance of approximately 1.1 million kilometers from Earth, Resilience continued its journey towards the Moon.
The critical orbit insertion maneuver was executed on May 6, 2025 UTC, involving a 9-minute burn of its main thruster, the longest burn to date for this mission. This maneuver was performed from the Mission Control Center in Tokyo, affirming the operational capabilities of a space engineering team. With the successful entry into lunar orbit, Resilience has now completed 7 out of the 10 defined milestones for Mission 2.
Significance of the mission. The Resilience mission is not only a technical demonstration but also carries a variety of payloads aimed at exploring and utilizing lunar resources. Among the payloads are 1. Water electrolyzer, developed by Takasago Thermal Engineering Company. This equipment will explore the potential for water extraction on the Moon. 2. Food production experiment, a self-contained module from Ljubljana Company,
aimed at investigating sustainable food production in space. 3. Deep Space Radiation Probe, developed by the Department of Space Science and Engineering at National Central University in Taiwan. This probe will analyze radiation levels in deep space. 4. TENACIOUS Micro Rover, a rover developed by ispace Europe designed to explore the lunar surface and collect regolith for analysis. 5. Cultural artifacts. This includes a UNESCO memory disk preserving linguistic and cultural diversity and a model house called Moonhouse created by Swedish artist Michael Genberg. The lander is scheduled to attempt a lunar landing no earlier than June 5, 2025, and has been designed to land near the center of Mare Frigoris at approximately 60 degrees north latitude.
Lessons learned in future prospects. This mission builds on the lessons learned from a space first mission,
which ended in April 2023 when the lander crashed during landing due to software issues. The successful execution of the orbit insertion maneuver demonstrates ispace's ability to leverage operational experience effectively and improve its technology for future missions.
Takeshi Hakamata, founder and CEO of ispace, expressed pride in the team's accomplishments and emphasized the importance of thorough preparations for the upcoming lunar landing.
The ability to conduct precise maneuvers and maintain a stable orbit reflects ispace's commitment to advancing lunar exploration and resource utilization. Looking ahead, ispace has outlined ambitious plans for future missions, including a third mission featuring the Apex 1.0 lunar lander expected to launch in 2026.
Additionally, the company is collaborating with NASA and Japanese space agencies to explore opportunities for resource development and scientific research on the Moon. Conclusion. The successful entry of the Resilience lunar lander into lunar orbit is a pivotal moment for ispace and the broader landscape of commercial lunar exploration. It not only reinforces the company's commitment to advancing lunar technology but also sets the stage for future endeavors that aim to explore and utilize lunar resources sustainably. As ispace prepares for the upcoming lunar landing, the global space community watches with anticipation, eager to witness the next chapter in lunar exploration.
The successful entry of the Resilience lunar lander into lunar orbit on May 7, 2025 is a remarkable achievement for ISpace, especially considering the lessons learned from its previous mission, which ended in failure. Here are some counterintuitive points and insights from the content provided. 1. Learning from failure. The Resilience mission's success is largely attributed to the experiences and failures of its predecessor mission. While one might expect that a mission that ended in a crash would deter further attempts, ISpace has effectively used the lessons learned from Mission 1 to enhance the performance and operational strategies for Mission 2. This demonstrates a critical aspect of resilience, the ability to adapt and improve after setbacks. 2. Low-energy trajectory. The decision to take a low-energy trajectory for the journey to the Moon, which is counterintuitive given that more direct paths often seem more efficient, highlights a shift in thinking about orbital mechanics and fuel efficiency. By minimizing propulsion needs, ISpace was able to conserve resources and increase the likelihood of success, revealing that sometimes less aggressive approaches can yield better results in space exploration. 3. Hit commercial payloads as a priority. The inclusion of various commercial payloads such as a water electrolyzer and a food production experiment emphasizes a growing trend in lunar exploration where commercial interests are aligned with scientific goals. This could suggest that the future of space missions may rely more heavily on private sector partnerships, which can seem counterproductive to traditional governmental space agencies but may actually enhance innovation and efficiency. For cultural artifacts in space missions, the presence of cultural artifacts such as the UNESCO memory disk and the Moonhouse model created by an artist in a scientific mission may seem trivial at first glance. However, this blending of art and science serves a dual purpose. It enriches the mission's narrative and establishes a symbolic connection to humanity's cultural heritage in the context of space exploration. This approach could redefine how we perceive the objectives of space missions beyond mere scientific and technological endeavors. 5. Resource ownership agreements. The agreement to transfer ownership of lunar regolith collected by the TENACIOUS rover to NASA for a nominal fee of $5,000 highlights a novel and somewhat controversial aspect of lunar resource utilization. In a field where ownership and rights to extraterrestrial resources are still being defined, this agreement indicates a shift towards legal frameworks that could govern space exploration, which may not align with traditional views on property rights. 6. Broader implications of commercial space exploration. The success of a space mission amidst a backdrop of increasing commercial involvement in space exploration suggests that the landscape of lunar exploration is undergoing a fundamental transformation. While traditional models have relied heavily on governmental agencies, the emergence of companies like ISpace indicates that the future could be more collaborative and competitive, leading to rapid advancements in technology and exploration capabilities. In summary, the successful lunar orbit entry of the Resilience lander is not only a technical achievement but also a reflection of how failures can lead to greater resilience, the innovative approaches in resource management, and the blending of commercial interests with cultural significance in space exploration. Such insights challenge conventional wisdom about space missions and could influence future endeavors in the field. The successful entry of the Resilience lunar lander into lunar orbit represents a significant achievement in commercial space exploration, but several important aspects of this milestone may be overlooked by the general public and even by industry professionals. Here are some critical elements to consider. 1. Learning from past failures. Significance. The Resilience mission marks a pivotal learning curve for ISpace, especially given the failure of its first mission, which ended in a crash due to software issues. This experience has likely shaped the operational protocols and risk management strategies for Mission 2. The ability of ISpace to leverage lessons from past failures demonstrates resilience not just in the mission's name but also in its operational philosophy. Why it matters. Understanding how companies adapt from failures is crucial in high-stakes industries like aerospace. It highlights the iterative nature of technology development and risk management, emphasizing that setbacks can lead to stronger, more informed practices in future endeavors. 2. Cultural and scientific payloads. Significance: the payloads on resilience include not just scientific instruments but also cultural artifacts, such as a UNESCO memory disk and the Moonhouse model. This aspect reflects a broader vision of lunar exploration that encompasses not just the scientific community but also cultural and artistic expressions. Why it matters: including cultural elements in space missions can foster a sense of global heritage and human connection to space exploration. It signifies a shift towards making space not just a domain for scientific inquiry but a platform for celebrating human culture and creativity. This could influence public interest and investment in space initiatives. 3. Commercial partnerships and future collaborations. Significance: the involvement of multiple commercial partners and the mention of future collaborations with NASA and Japanese space agencies indicate the growing trend of public-private partnerships in space exploration. The mission's success could pave the way for more robust commercial endeavors in lunar resource utilization. Why it matters: observing how commercial entities like ispace collaborate with established space agencies may redefine the landscape of space exploration. It highlights the importance of leveraging diverse expertise, resources, and technologies to achieve common goals, potentially leading to more efficient and innovative approaches. 4. Resource utilization focus. Significance: the mission's objective includes technology demonstrations for resource extraction such as lunar regolith collection. This is part of a broader strategy to establish sustainable operations on the Moon, which is essential for future exploration and potential colonization. Why it matters: the focus on resource utilization underlines the long-term vision for humanity's presence in space. As missions aim to extract resources from the Moon, it raises questions about property rights, governance, and the ethical implications of exploiting extraterrestrial environments. This aspect is critical as it lays the groundwork for future economic activity beyond Earth. 5. TENACIOUS micro rover. Significance: the deployment of the TENACIOUS micro rover, designed to explore the lunar surface and collect regolith, is not just a technical achievement but also a step toward autonomous exploration. The rover's ability to relay data back to the lander emphasizes advancements in communication and data collection in remote environments. Why it matters: autonomous rovers can significantly enhance exploration capabilities, allowing for more extensive surveys and data collection without the need for constant human oversight. This technology could be pivotal for future missions, enabling more complex exploration tasks and reducing risks associated with human spaceflight. 6. Critical maneuvers and operational planning. Significance: the successful 9-minute burn of the main thruster to achieve lunar orbit is a testament to meticulous planning and execution. The precision required for such maneuvers is often underestimated in public discourse. Why it matters: understanding the complexity of orbital mechanics and the precision required in spacecraft operations can foster a greater appreciation for the engineering challenges involved in space missions. It also highlights the importance of rigorous testing and simulations to prepare for real-world applications. 7. Impact on global space exploration landscape. Significance: the success of the Resilience mission positions ispace as a key player in the burgeoning commercial space sector, setting a precedent for other companies looking to engage in lunar missions. Why it matters: the emergence of commercial space exploration can democratize access to space, leading to more diverse participation in aerospace activities. This shift may stimulate innovation, reduce costs, and increase the pace of technological advancements in space exploration. Conclusion: the Resilience lunar mission is much more than a successful technical operation. It encapsulates lessons learned from past failures, cultural integration, strategic resource utilization, and the evolving dynamics of public-private partnerships in space exploration. By overlooking these critical aspects, one misses the broader implications of this achievement for the future of humanity's endeavors in space. As the landscape of lunar exploration continues to evolve, understanding these nuances will be essential for stakeholders across the spectrum, from policymakers to industry leaders and the public. 1. Successful lunar orbit insertion and mission milestones. The Resilience lunar lander achieved a critical milestone by successfully entering lunar orbit on May 7, 2025.
This marked the completion of the 7th out of 10 key milestones in its mission 2. Part of the HAKUTO-R program. The precision maneuver involved a 9-minute burn of the main thruster, showcasing ispace's ability to conduct complex operations in space. This success demonstrates the lessons learned from the previous mission, which ended in a crash, and highlights the importance of meticulous planning and execution in space missions. 2. Technological demonstrations and scientific payloads. Resilience carries several innovative payloads, including a water electrolyzer, a food production experiment, a deep space radiation probe, and the TENACIOUS micro-rover, which will collect lunar regolith. These payloads not only serve commercial interests but also contribute to scientific research and technology demonstration aimed at understanding and utilizing lunar resources. The inclusion of a UNESCO memory disk and a cultural artifact, the Moonhouse, reflects the mission's broader goals of cultural preservation alongside scientific exploration. 3. Strategic partnerships and future missions. The mission underscores a space commitment to lunar exploration in collaboration with NASA and other international partners. The company has plans for subsequent missions, including the Apex 1.0 lunar lander in 2026 and a Japanese-built lander in 2027. This strategic expansion highlights the growing role of private companies in space exploration and the potential for commercial partnerships to drive advancements in lunar resource utilization and exploration. 4. Implications for commercial lunar exploration. The successful entry into lunar orbit signifies a pivotal moment for ispace and the commercial space industry at large. It signifies a step forward in the commercialization of lunar exploration, with ispace positioning itself as a leader in providing low-cost transportation services to the Moon. The mission's success may inspire confidence in future private sector investments in space exploration, paving the way for more ambitious projects focused on lunar sustainability and resource extraction. This could have far-reaching implications for humanity's future in space. 1. Apollo 11 Mission 1969. The Apollo 11 mission conducted by NASA was a historic spaceflight that resulted in the first humans landing on the Moon. Launched on July 16, 1969, the mission culminated in the lunar landing on July 20, where astronauts Neil Armstrong and Buzz Aldrin became the first and second humans to walk on the lunar surface. The mission demonstrated remarkable resilience in overcoming technical challenges, including the need for precision in landing maneuvers and addressing potential risks during the mission. Armstrong's famous words, "That's one small step for a man, one giant leap for mankind," captured the monumental achievement of lunar exploration. 2. Mars Exploration Rover, Spirit and Opportunity 2004. NASA's Mars Exploration Rover mission, which included the rovers Spirit and Opportunity, was a significant milestone in planetary exploration. Launched in 2003, both rovers were designed to operate for 90 Sols Martian days but exceeded expectations, with Opportunity operating for nearly 15 years. The mission demonstrated resilience as the rovers navigated the harsh Martian environment, conducted scientific investigations, and provided valuable data about the planet's geology and potential for past life. The ability to adapt to unforeseen challenges and extend the mission's life exemplified human ingenuity and determination in space exploration. 3. Voyager Program 1977-present. The Voyager program, launched in 1977, consists of two spacecraft, Voyager 1 and Voyager 2, designed for long-term exploration of the outer planets and beyond. Both spacecraft have traveled farther from Earth than any other human-made objects. The resilience of the Voyager mission lies in its ability to function and send back data for decades far beyond its original mission parameters. Voyager 1 entered interstellar space in 2012, and Voyager 2 followed in 2018. The program has continued to provide invaluable scientific knowledge about our solar system and the interstellar medium, demonstrating the longevity and adaptability of NASA's engineering and scientific efforts.
The successful entry of the Resilience lunar lander into lunar orbit marks a pivotal moment for space and the broader landscape of lunar exploration. As we look ahead, several key predictions can be made regarding the future of lunar missions, commercial space exploration, and the technological advancements that will stem from this historic achievement.
1. Increased commercial participation in lunar exploration. The success of the Resilience mission will likely inspire more private companies to engage in lunar exploration. As space has demonstrated, commercial entities can effectively collaborate with governmental space agencies such as NASA and JAXA to push the boundaries of space exploration. We can expect a surge in investments in lunar programs, leading to a more competitive market where companies vie for contracts to deliver payloads, conduct research, or even establish lunar bases. 2. Advancements in lunar technology. The payloads carried by Resilience, including the water electrolyzer and food production experiments, signify the beginning of practical applications for lunar resources. Future missions may focus on developing technologies that utilize lunar materials for sustaining human life. This includes refining in situ resource utilization (ISRU) technologies to extract water, oxygen, and other essential materials directly from the Moon's surface, paving the way for long-term human habitation. 3. International collaboration on lunar missions. The achievements of Resilience will likely lead to increased collaboration among nations for lunar exploration.
As countries recognize the Moon's potential as a resource hub, we can anticipate multinational partnerships similar to the International Space Station (ISS) model.
Shared missions will enable countries to pool resources, share technology,
and distribute the costs associated with lunar exploration. 4. Establishment of lunar bases.
With successful landings and resource utilization technologies in place, the groundwork will be laid for establishing permanent lunar bases. These bases could serve as research outposts, tourist destinations, or platforms for further explorations to Mars and beyond. The timeline for such bases could begin as early as the late 2030s, contingent on the success of upcoming missions. 5. Enhanced scientific research opportunities. The data collected from Resilience's payloads, particularly the TENACIOUS micro rover, will provide invaluable insights into the lunar environment.
As more scientific instruments are sent to the Moon, researchers will have the opportunity to study lunar geology, the effects of deep space radiation, and the potential for growing food in extraterrestrial conditions. This research will not only contribute to our understanding of the Moon but will also inform future missions to Mars and beyond. 6. Cultural and educational impact. The inclusion of cultural artifacts like the UNESCO memory disc in Moonhouse by Michael Gendberg highlights the Moon's potential as a venue for cultural exchange and education. Future missions might prioritize cultural preservation alongside scientific exploration, leading to initiatives that engage the public and inspire the next generation of scientists and explorers.
7. Regulatory frameworks for lunar resource utilization.
As commercial interest in lunar resources grows, there will be an urgent need for international regulations governing the extraction and use of lunar materials.
Discussions among spacefaring nations will likely intensify, focusing on establishing a legal framework that addresses ownership, environmental protection, and sustainable practices. 8. Development of lunar infrastructure. Alongside human exploration, the development of infrastructure will be critical. Future missions will likely focus on building landing pads, power stations, and communication networks on the lunar surface.
Such infrastructure will facilitate not only space missions but also those of other commercial and governmental entities aiming to explore deeper into space. 9. Advancements in spacecraft technology. The lessons learned from the Resilience mission will inform the design of future spacecraft. Innovations in navigation, propulsion, and automation systems will emerge as companies seek to reduce costs and improve mission success rates. We can expect to see a new generation of spacecraft that are more reliable and capable of supporting complex missions. 10. Pathway to Mars and beyond. Ultimately,
The success of lunar missions like Resilience will act as a stepping stone toward Mars exploration. The technologies and knowledge gained from lunar missions will be essential for planning crewed missions to Mars and establishing a human presence on the red planet. As companies and governments prepare for Martian exploration, the Moon will serve as a critical testing ground for technologies and life support systems. Conclusion. The successful entry of the Resilience lunar lander into lunar orbit is not just a technical achievement, it represents a new era in space exploration. As we move forward, we can expect a dynamic and collaborative approach to lunar exploration marked by technological innovation and a shared vision for humanity's future in space. The next decade will be crucial in shaping our understanding of the Moon and its potential as a resource for sustaining life beyond Earth.